For my Lab 5, I chose to analyze and model the motion of a slinky after it was dropped from static equilibrium. One reason I was interested in this problem is that I find slinkies fascinating simply as an object, and I thought it'd be pretty cool to be able to model one of the strange things they do. A slinky is a tension spring, a spring whose relaxed length when it's essentially collapsed. This lack of compression force is what gives a slinky its unique dynamics, but it also presents some problems when modeling. I'll discuss the physical properties of slinkies in a moment. One of the main questions I was interested in was how was the velocity of the top of the slinky influenced throughout the fall? If we dropped a single ring of a slinky, it would accelerate due to gravity until it reached terminal velocity. In the video, I could imagine it slowing down and then speeding back up every time a new turn was encountered, or maybe it accelerated due to gravity because the turns below it had already started moving because the spring tension force had already decreased to the extent that they could move. This question of acceleration fascinated me. As in other labs, I first analyzed the video and tracker and then looked at the resulting graph of movement in the y direction. I then attempted to understand the dynamics at play by reading several papers and articles about the phenomenon. Finally, I used physics principles that we have already used in previous labs to create a series of computational models which approximate the motion observed in the video. I know from my reading that none of the models are really very good, but they roughly model some of the interactions we observe between the slinky and its surroundings. All of the models rely upon the interaction of the spring governed by Hooke's law and finite distributed masses, which are pulled by the springs in various directions. The paper's authors also pointed out that the mass distribution along the spring when it is in static equilibrium is not symmetrical from top to bottom. That is, the center of mass is not halfway between the two endpoints. They modeled this using a variable called psi, but I was unable to effectively put this mass distribution into my model. This plays a significant role in one of my models, and the implications of the placement of mass along the spring will be discussed later. Here's the tracker analysis. As you can see, I track both the top and bottom. In the lower left, you can see the y component of the top's velocity. The bottom also stays relatively stationary until it is impacted by the top. The paper of Cross and Wheatland presents complex equations for modeling the motion of the slinky. I was unable to include many of the finer details, but a few things I learned were that the time it takes for the change in tension to propagate down the spring is given by the formula the square root of the mass over the spring constant k, and for most springs is about 3 seconds. This time was approximately verified in my model. For my first model, I envisioned a series of 10 masses connected by massless springs hanging at rest. This is similar to a slinky hanging at rest, but it is a simplified version which uses objects I'm used to modeling. For each mass, there is a gravitational force. For the first mass, there is only a spring force pulling down, and for the last mass, a spring force pulling up. For the other masses, there are spring forces pulling both from the top and from the bottom. In this way, the release of the tension propagates down the spring. Then, as in other labs, I use Newton's second law to iteratively calculate using Fnet the new position of each mass in a while loop. Here's that model running. This model has some major problems, perhaps the worst of which is my inability to correctly model the weight distribution along the spring. What you see here is an approximation based on my observations of tracker video, but they ought to be governed by a formula based on the magnitude of the weight force that is exerted on each mass along the spring. This would definitely be something to figure out in a later iteration of this model. As you can see, particularly in the graph, the bottom actually starts moving up a bit due to the values for k being slightly too high. I was unable to get a model with 10 masses to work just right because the incorrect weight distribution caused problems for updating the position. In addition, I had trouble with objects passing through each other. Figuring out a way to make sure that didn't happen would also be a big improvement. Finally, I created another model which suspends a single mass from a long spring. This one, however, introduces a drag force. Using a similar iterative calculation loop and a very small time step, you see a different model which leads to the same conclusions as the previous. The movement we observed in tracker satisfies Newton's second law as well as Hooke's law. Here you can see a graph of the velocity of the top of the spring for each model as well as the tracker analysis. From the modeling process, I know that the top mass should accelerate very rapidly at the beginning because it has both downward gravitational force and a downward spring force acting on it. After this spring force is diminished, the object begins to fall more slowly as it encounters the other objects in its way. My first model correctly models the beginning behavior, but the later decrease in velocity is probably more due to the eventual increase in tension from Hooke's law after the mass passes through the object below it. This would of course not actually happen in real life. The second model, which was created using only the dynamics of a falling spring inherent in VPython, is not accurate. The movement observed and that modeled in Model 1 is similar to that modeled in the paper of Cross and Wheatland, so I'm hopeful that the concepts behind my first model can lead to a fairly good imitation of the slinky's motion. Thanks for watching.